intention is to kind of make you think about this area and about this question in a bit different way. Okay, so let's talk about that. So like, let's start with the most important thing here, like why we are even here. It's essentially, let's talk about our love of deep learning. So why do we love deep learning? So we actually spend the time inside as opposed to outside. Well, there are many reasons to love deep learning. One of them are these all really cool applications that kind of really inspire us, and kind of this is, how our world will be better once these things are more prevalent. That's clearly one way. The other way is that they have these cool applications and these cool videos, like self-driving cars and whatever. Essentially this all is just, this is the world we should strive to live in. No question about that. And there is even more reason to love deep learning. Another reason is that actually it tends to do the most important thing in the world. It is, optimizing the accuracy on ImageNet dataset. That's also a very important task. And also, actually, the other thing that people really like, deep learning for is that somehow the way the representation actually learns. Okay, so we have this kind of mythos of kind of that the way this deep neural network learns is that essentially, like at each level of the network, it kind of is learning like more and more advanced features, more and more high-level features. And this is something extremely appealing and kind of very much resonating with any human. So these are the reasons to love deep learning. However, I must admit, at least for me, that this is a very difficult love, okay? Because essentially, as much as I would like to love deep learning for all of these reasons, each time you look a little bit closer, you realize that things are not exactly right, okay? So for instance, in terms of application, as much as, Teslas are cool when they actually work, they sometimes don't. And they sometimes don't in a very disturbing way. So here is just a Tesla car that is trying to run into the divider, and the driver has to take over to avoid collision. And even on ImageNet, you have pictures like that. So the correct classification here is that this is an insect, if you didn't know. But for some reason, the model insists this is a dog. Okay, and it's not clear to me why would it make such a mistake. It's able to distinguish between very precise breeds of the dog, and for some reason, this is also a dog to it. Okay, and also, even if this representation actually turned out to be quite nice, they kind of are not exactly what they seem. So in particular, it's very much not hard to have kind of pictures that essentially are mapped to essentially the same representation, but of course look completely different. Okay, so whatever is the internal representation that these models use, it's not exactly aligned with how we humans would like to think about it. Okay, so these are the kind of the problems, and of course the question is what's going on. And I hope that in this talk, I will convince you that many of these problems stem from the one reason or one phenomena, namely the phenomena of adversarial robustness and essentially the existence of adversarial perturbations. Okay? So here, of course, we have the right example of adversarial examples. I'm still offended that in the other example you use the panda. So we will talk about that after the talk. Of course, why this is the best example? Because you can say the usual joke about this, that this is how machine learning can learn the pigs to fly. Essentially, like I'm not sure what is the joke for the other example. But yeah, but this is kind of as funny as it is. Kind of we already know, and that's thanks to to Ziko's great talk. We know that there is kind of something really serious beneath. Right? In particular, we know that somehow what it really tells us is that the way our model generalize is maybe not the way we would like them to generalize. And in particular, if you wanted to fix this kind of glitches, which again can actually give rise to real problems, you might want to think about something that we call adversarial robust generalization, essentially in which kind of you would like to have a classifier that still has good prediction, even if you look worst case over all the possible perturbations that you would like this classifier to be robust. Okay, so again, similarly to Ziko, I don't want to get into what this exact class of perturbations should be. I might comment on this towards the end, but the point is that there are some natural invariances you would like that any reasonable model should have, and somehow you realize that unless you ask for it, you actually don't have it. So this is the way to actually explicitly ask for it. Okay. And so this we realized is to be a goal. It took a bit of a while to actually start getting towards this goal, but as already it was clear from Ziko's talk, we are actually succeeding somewhat in getting there. So this is all great, and in particular, so we are able to start getting some models that are robust in at least some weak sense, but this weak sense was something that seemed to be hard to achieve just a year ago, so we are making fast progress. And also we are starting to learn about what does change about ML as we go from kind of the standard understanding of ML, where we just don't worry about these adversarial perturbations, to an ML that actually is guaranteed, or is supposed to be guaranteed to be robust to them. So the things that we discover is, first of all, that the training of this kind of models becomes harder. And also, like, sometimes this is actually not necessarily true for Zico's randomized smoothing approach, but kind of we definitely have to work harder to train this model. So if you want to use robust training, it's a more expensive procedure. You need larger models, and essentially things become difficult. The other things that we actually realize is also that these models, even though they kind of become robust, they also seem to sometimes necessarily sacrifice something. So essentially, they sometimes need to actually, compromise standard accuracy. Okay, you have to necessarily pay this price. And also, we learn that kind of sometimes to actually even be able to get a robust classifier, you actually might need more data than what you need for standard, like to just get a standard generalization. So there is also this kind of other information theoretic limitations. So we are learning and discovering all these things, and this is cool. But somehow, as happy as I am about this progress, there was and actually still is a little bit of discontent that I had. Essentially, we start to understand how and what. So essentially, how to get robustness and what kind of being robust means. But somehow, I still could not convince myself that I know why. Okay. In particular, essentially, the one mystery that I had was, why adversarial perturbations exist in the first place. Maybe this is not that surprising. What is more surprising is why they are so widespread. Okay, this is what I really found surprising. Also, even bigger mystery to me was why these perturbations tend to transfer. So there's this phenomena that I might choose a kind of a perturbation that fools one model, and then I use exactly the same perturbation to fool another model. To attack another model, and it usually works. And this didn't make sense to me, why this is the case. I understand that a given model might be fooled by just leveraging some of the glitches of it, but why the same kind of trick works for very different models with different architecture trained even on the independent sampling of the data? Why is it happening? The other thing is why robust training works. And again, there are some intuitions that are coming from optimization, but these intuitions have some leap of faith. And kind of it still is unnerving me a bit. Why what is really happening there? And it is even somewhere for randomized smoothing, even though there was a very nice intuition that Zico presented, somehow I think that at least there's maybe we know why it works, but I would like to show that there is also a different way of looking at it. Okay? So this is the question. And let's just start with trying to answer the first one. Okay? So why are our models brittle? And of course, this is a question that was asked over and over, and different explanations have been offered. Some of them say that this is the reason is here that we are working with high-dimensional models and in high-dimensional, domain. Others say this is just some kind of statistical fluctuations showing up. Another one say that this is of course, this is just we are optimizing for expected performance, and here we measure worst-case performance. So what would you expect? There are also people who claim that this is some kind of punishment that we get for using ResNets. That's also a valid theory. But somehow what all of these explanations have in common that they really view adversarial examples as an aberration, something that if we did our training right, or if we do our training right, they will go away. Okay, so even this very interesting work that Peter mentioned, that essentially they might be an artifact of us being over-parameterizing and interpolating the data. In some ways, you could imagine that if you then don't interpolate the data and you kind of generalize in a different way, then adversarial examples might go away. Okay, this could be conceivable in this case. So, okay, so let's think about it. But before we try to answer this question, let's actually try to think about what it is about adversarial perturbations that seems to unnerve us. Okay, so why we don't like them? Well, we don't like them because they lead to situations like here, where we have a beautiful picture of a dog. Then we add to it some meaningless noise that of very small magnitude, and suddenly we are getting this, essentially the same beautiful dog, but for some reason the model insists that that's a cat. That's definitely very, very annoying. And like that's why we kind of work hard to avoid these kind of things. But kind of the thing to realize is that this is annoying, at least so far, only because this is kind of a human perspective. Essentially, we as humans, we know what the dog is supposed to be. And we know that this is a meaningless noise. And this should be dog as well. Because that's, we as humans, we have these priors, and we know that this is how world works. So, from our perspective, when we kind of solved one of the most important problems in the world of like distinguishing cats and dogs, essentially, well, we know how you should solve this task, right? Like you should look at this kind of different features, snout, ears, and based on that, you will be able to tell, is it a dog or is it a cat? And these are really the things that matter for this classification task. However, even though this is a very natural human perspective, if you try to zoom out and think about ML perspective, you might start to wonder. Right? First of all, from the point of view of this, of this poor neural network, for it, this image is meaningless. It's just a collection of pixels. It's just a vector of values. It has no idea what a dog means. To it, dog is just a label. Essentially, it doesn't have any intrinsic meaning in it. And there is only one thing that this poor network is trained to do, is to maximize its accuracy on the test. Essentially, it will just. So essentially, like the better way to think about it when you think about it from a machine learning perspective is not to think about distinguishing between dog and cats, but imagine that you as a human would be given the task of, there are two classes, tap and talk, which have no meaning to you, and you get this kind of collections of pixels, and your job is to distinguish between them. Okay, and then you stare maybe enough into them, and you realize, oh, there is a pattern. Like there maybe if this kind of segment appears that this is one class, if this segment appears in the other class. But this is should be a really better way of you trying to align, what it really means to a machine learning model to try to solve this problem. Okay. And now, if you look at the example, so to us, here is this kind of the annoying thing about, about this. This is how we look at adversarial examples and are annoyed by this. But from the point of view of the machine learning classifier, kind of the picture might be like this. Essentially we have an instance of a class tap, then you mess up some of the rectangles. And then you have an example of a class talk, and for some reason this is supposed to be annoying. Okay, well, I'm pretty sure that you are much less annoyed by this part than by this part. And in particular, one thing that you should question immediately now is saying, even if you look at this, at this perturbation alone, is this perturbation really meaningless? Essentially now everything is meaningless to you. Why do you think that this perturbation is meaningless as well? So let's think about it. So this is the question. So are adversarial perturbation just some kind of meaningless artifact that kind of finds some nooks in the model and kind of try to fool it? And here's the simple experiment. So what I will do is I will take a standard cat versus dog training set. And what I will do is I will look at every single example in this training set. And I will find the adversarial perturbation for I take some good model, and I take adversarial examples. So essentially, I attack each of the image to make it to be to convince the model that it is this is an input from an opposite class. So every dog is a cat, and every cat is a dog. Okay, so that's what I do. And now what I do is after attacking each of these inputs, I actually create a new training set, in which I take this kind of perturbed version of the image, and actually I put the new label to be whatever the adversarial perturbation suggested it is. Okay, so this way I have a new training set, which is essentially this mislabeled adversarially perturbed version of the original training set. And what I do is I train a fresh classifier on this new test set, on this new training set. But then I will do something weird. I actually test it on the original test set. Okay? So essentially what we are doing here is we are training classifier on a data set that is completely mislabeled. There is essentially not a single human recognizable dog that is labeled as dog, and not a single human recognizable cat that is a cat. Still, for some magical reasons, we want to test it on we want it to learn the concept of a cat and concept of a dog properly. So, what do you think will happen?
So just a quick question, clarifying. So you're moving the image along the direction of the gradient. That's how you.
Yeah. So you find whatever. We just do the simplest thing. Yes. This is a non-robust model. So you just take you find the direction of the gradient that will kind of in what direction you have to move the image to change the class in most efficiently. and essentially that's what you do. Like you just push a little bit, you don't have to go far, and you find the specification.
You're doing one step, or you're doing like?
We did it just one step. Like whatever it took to just fool the model. It's a not robust model, so it's very easy to like to fool. Okay. So what will happen?
Yes, you do well.
You will do well. And essentially what you will actually get a non-trivial accuracy on the original task. Actually, you will get something like like on CFAR, cats versus dog, you get 78%. Okay? So think about what happened here. It's like it's not only that, it's not even that we have a noisy data set. We just had a data set that claimed that there is to a human, if a human never saw a dog or a cat, you would show this the data set, they would be convinced that dogs are cats and cats are dogs. So you give such a training set to a classifier, and somehow magically it figures out that this should be the opposite. Okay? So what's going on here? Well, kind of the only explanation that we could come up with, and I think this is the right explanation, is that maybe there is something in our mental picture that we got wrong. Essentially, that when we kind of thought, like we paid a lot of attention to how the prediction of the model changes when you try to perturb it, but we did not really pay too much attention to what the perturbations are themselves. And actually, maybe these perturbations are not some kind of random, weird aberrations. Maybe they actually are meanings. And in particular, maybe they don't correspond to just like doing some mindless manipulation of the model. Maybe they correspond to changing some important features in the data.
The alternative explanation is that you really trained it to imitate the original network.
Yes, that would work.
Imitates the original network.
That would work if the network I use the classifier on would be the same architecture. We use a completely different architecture, it still works. But that would be one thing. That's something we also thought at first, that essentially you're doing like model distillation, where you kind of, it's kind of you encode the weights of the model in the way things are labeled. But yeah, we just use totally different architecture and so on, and it still works equally well. Okay, but that's a good question, and yeah, this we ruled out. Okay, so essentially, like the way we conceptualize is just the following: is somehow the way maybe we should think about how classification happens is that there is kind of two kinds of features in our data set. Okay, one of them are the kind of what we call robust features. So essentially, there are features that that correlate well with the label and are robust even if you try to perturb the image a little. Okay, so this is in particular things like ears and snout. If you just like add a bit of L to nose, they will still be ears and snout, and they will still correlate well with the image. And that's how we thought about things. That's how we think about about learning as humans. However, what was interesting is that we actually discovered that there is there are also this kind of there are patterns that correspond to non-robust features. So features that actually are genuinely predictive of what is the right label. They actually do generalize, but they are extremely brittle to perturbations. And essentially what happens is that when, the only thing that the model wants, it just wants to do as well as possible on the test set. So any feature that is correlated well with the label is a good feature to use. And it turns out that these non-robust features are actually really great. They actually correlate very well with the label. Like we have seen it actually when the model had like, the robust features were telling it one thing and non-robust features were telling it other things, the model actually trusts non-robust features more. Okay? And essentially that's why, because the non-robust features are so good, our models tend to pick on them. And that's how they expose themselves to be vulnerable to adversarial perturbations. Okay?
Quick question. So robust features for a dog would be labeled as cats.
Yes.
Right? But then how does it know that it's not a cat in the test?
Yeah, so what happens is essentially, I will go through this example again, and then we can answer your question, but that's a great question. So yeah, so let's just take a second look at what actually happened with this kind of robust and non-robust features in mind. So we had our training set in which kind of both robust features and non-robust features were aligned well with the correct label. Now when we created the new training set, what we did is somehow now the robust features are essentially thinking of a different thing. They still claim this is a dog, even though the new label is cat, while the only non-robust features are actually consistent with the new label. Okay, so essentially like the all robust features are misleading, and non-robust features are actually the one helpful. And in some ways, now there is some kind of confusion that the model has, right? But essentially this confusion, since it kind of trains, it realizes, okay, these features are like in some ways anti-correlate. So essentially what is happening is that kind of the non-robust features, they have better correlation with the right label, so it chooses to rely more on them. And yes, these things are confusing. And maybe it ignores them, maybe it kind of realizes they are anti-correlated or something like this happens. But somehow the fact that non-robust features alone are already good enough to correlate with the right label kind of allows it to get the bulk of the prediction. By the way, remember that the prediction accuracy we got is 78%. It's of course impressive that you can get anything better than 50%, but it's not what you would get if you actually train on this on this training set alone.
But it could have easily thought that the robust feature of that dog could have been airplane or a penguin, right? How does it know it's...
Oh, wait. So here we just talk about the binary classification. So this is just, there are just dogs and cats here. Yeah. If you do it on full 10, like the similar phenomenal things, but yes, but then like, yeah.
Do you know if you picked like another pair of classes that were like visually, you'd say maybe more dissimilar with each other, you see the 78% drop? Like, is it sensitive at all to like kind of?
We did not do that. Like, we tested different classification tasks, but we did not do this kind of analysis. So
I'd expect it still does well. I'd just be curious to know.
Well, we expected to again. The classification tasks we did test on all had the similar conclusion, but we did not look yet into the fine-grained thing exactly how these things actually work.
If you subset to adversarial examples that you already know transfer well as your training set, does this improve the?
We did not do that, but there are some experiments that are not done by me. It's not published yet that seem to suggest that. So there's I will get back to transferability in a moment, and that's a. But yes, like our hypothesis, it's not confirmed. Like, well, there are some, again, not our experiments that kind of seem to confirm it, is that, yes, the transferable adversarial examples are really the ones that correspond to features. There is also a part of it, this is just some aberrations, and they don't transfer well. Okay, so in particular, it is possible, so this is Pritum Nakaram did these experiments, and you can actually construct adversarial examples that do not transfer. And when you do these experiments with this non-transferring adversarial examples, like, this doesn't work. Which shows that yes, so essentially like transferability seems to be intimately tied with being the kind of meaningful perturbation of non-robust features. Okay?
What is the definition of robust features? How do we know that they are?
Okay, so robust features means that you are actually like, okay, so this is actually a good discussion to have after offline, is essentially these are the function of the data set that the model picks up on that are correlated with the right label, but you can flip them by perturbing the input, within the, like, let's say, L2 ball.
But we don't know that the network actually has any robust features.
I think let's take it offline. I think this is a good discussion, but yeah, like we spend a lot of time talking about this because but I will get to this. By the way, we don't know how these non-robust features look like. Like we know they exist, we have no idea how they actually look like, so this is essentially the thing here. So essentially, that's why this experiment come.
You say you know they exist. Back to these two questions. I mean, you hypothesize them, and you got the 78%. But how do you know they exist? I mean,
so we did more experiments.
Control, right? If you do an adversarial perturbation in the direction of an airplane or refrigerator, that's a control to test that hypothesis that they exist.
I know, like we did more experiments than that. We are kind of, we can talk offline about more experiments. No, but like we don't because when you make such a thesis, you agonize that it's wrong, and exactly like so that's why we tested. We did more experiments than what I just did. This was not like, oh, this is the experiment and we are done. There is more. I'm still welcome everyone to try to disprove it because I would. If there's a different explanation, I want to know.
And couldn't you just think of the neural, like the functions learned by the neural network as themselves the non-robust features? Like
they are, but
they are features of the input that are flippable. Like
so by definition they are. Like this is our definition, but it's not like you would like to understand something more about them. It's like, is it some kind of configuration of pixels? Like clearly, by definition that's what they are, but you would like to have more concrete definition of what they are. Again, we can talk about it more. So I guess the point here is that I think the important point here is that there is kind of this difference between the human and ML models prior, that kind of we have this human perspective of how we should learn. And so we had heard that this is the only way of learning, but it turns out that there are either like different ways of actually doing well on standard generalization, and maybe that's what our models actually are doing. So there's kind of this, there's no reason a priori for us to expect the model to prefer this way of learning, if this way of learning actually might lead to better generalization performance. Okay, so in particular, this also means that adversarial examples are a human phenomenon, and also, if you want to have interpretable models, then essentially, you have to think about it at the training time. Because if you just train a model in a standard way and then you want to explain it to a human what it's doing, well, then if the model is using non-robust features, we don't know as humans what these features are and how to make sense of them. So you either have to ignore that part of the decision process, or you are not able to find a human understandable explanation of why model works. And so if you really wanted to do kind of the more human-like model, you have to, at the training time, kind of try to force the model to learn the way the humans learn, as opposed to the model that, the way that leads to the best generalization performance. Okay, so this is kind of the hypothesis. So what now? So it definitely, at least to me, gives a new perspective on adversarial robustness, and also provides insights into many other questions that I mentioned. Okay, so in particular, one cool corollary of this is that there is a new capability you can do. So essentially, what you can do is you can take a data set, and then you can essentially use the robust model to create its robustified version. So this is like a different version of the data set, such that essentially once you have this training set, you can just train the model in a standard way. And it actually will not only get will learn the concept in the standard way, but also it will be it will do robust classification. So kind of the idea here is that what you do is essentially distill from the model. Like the only features that you transfer to this model are the robust models, are the robust features. So kind of this way you cleanse the data set from non-robust perturbations, and then the model, when it tries to learn, it has to only rely on robust features, and this actually leads to robust classification. Okay. So this is about the features, and in particular, there is a bunch of papers that claim that, the reason why we have adversarial vulnerability is because, we train with batch norm, and that's why it is, or we train with SGD, and that's why it is. And essentially, as long as, your claim is that this alone is the reason why we are adversarially robust, this data set is a counterexample to this. Because this data set, you can train with batch norm, with overparameterization, with whatever you want, you still will get robustness. So essentially, if you just want to explain by these techniques alone why things are vulnerable, it will not be true.
How comparable is this the standard accuracy and the robust accuracy to the?
It's worse. It's worse. There are significant drops. So this is just proof of concept. This is not the way to do it.
So how is this robust data set generated?
Essentially, yes. So.
Confusing, right? You just add perturbations along the confusing directions with the correct label.
So that's how you get a robust model. But now, once you have a robust model, how you get this? So essentially, what you do is can you ask me in a moment, because there will be a better moment for this to explain. But this is a very good question. That's kind of how you get there. So the other thing that is important is the transferability. So finally, now transferability makes sense to me, because if adversarial perturbations correspond to altering non-robust features in the data, then this is a property of the data set, not of the model that you learn. So essentially, if non-robust features are useful for this data set, many models will find them useful. So adversarial perturbations that just flip these non-robust features will all kind of work across all of these models. So finally, this makes sense to me. That this kind of explains why transferability is happening. And as I said, Pretum actually found the non-transferring adversarial examples, and then none of these effects that I said they come across.
So do you think then that these features, humans should actually learn and they're meaningful things, like actual, high frequency correlations, or is it like a small data set artifact still or something like that?
I don't know. That's I think the interesting question. And the question, I will get back to this question, but I don't know.
Yeah. So as far as we know, transferability doesn't happen across data sets? Like if one model is trained on, even the same task but a different data set?
I did not try that. What we did try, it does happen if you subsample the same data set. Like you get two different training examples by subsampling the same data set, it still transfers. But across training set, this is a good question. We are supposed to do it at some point, but we didn't, so I don't know.
There are some papers where it does.
So then it does. We didn't check it. I would expect if these data sets are similar, then probably but we did not look into it.
So maybe the non-robust features are more than a property of the data sets.
Yeah, well, we will get to that. That's a question. That's a very good question. Okay, so indeed, then we did experiments, and indeed, the things that transfer the most are exactly the things that essentially that there is a seems to be clear correlation between how robust the model, is, and how well things transfer, and kind of confirming this hypothesis. And also, if you look at what robust training, like it's another perspective of why robust training is useful. Essentially, as you remember, like what you do in robust training, you are kind of trying to do like robust ERM, where you essentially like always look at the worst case perturbation of the thing that you want to classify. And somehow now what really happens is that this procedure, what it does, it always makes sure that you can't depend on any patterns that can be changed by perturbations in delta. So essentially what you are doing, you are making the non-robust features with respect to this perturbation set to be useless to the model, because you always kind of punish the model if it tries to rely on them, because you clearly can flip this, these features and tell the model that it is wrong. Okay, so in some ways you are really making them explicitly any non-robust features, you make them useless by breaking the correlation with the correct label. Okay? And it's similar with the randomized, with the randomized smoothing. Essentially, like the intuition here is that kind of you are just adding noise to the input, and this noise overwhelms any of the signal that these features that are sensitive to perturbations actually convey. So you are essentially overwriting it, and that's why the model cannot learn from it, and then it just focuses on learning from robust features, and that's why how you get robust. Okay, so yeah, so this is the same conclusion. And also finally, like as I told you, there are some of these effects of kind of like of what we know how robust models behave. So in particular, remember, like if robust models can only use robust features, even though there are non-robust features that are helpful for generalization, then what happens that you need actually more data to get given accuracy, because essentially you are constraining the way the model can extract patterns from the data. And also you might be getting a lower standard accuracy, because again, if you give the same amount of data to two models and one of them is constrained in a way it can extract the patterns and other isn't, clearly there will be something worse. And of course the question is, even clearly, like, even if non-robust features give you better accuracy, standard accuracy, does it mean it's doing the right thing? Like in some way, this is exactly the question that you are coming from. Like essentially, like, should we depend on the non-robust features or not? Are there actually things we want to do? Like, are there some interesting insights that actually make sense? And if we were able to figure them out, we would use them? Or are there some completely meaningless patterns that we should avoid depending on? So for instance, like think about if you learn cats versus dogs from pictures on the internet, one correlation that you will probably find is that like cats are photographed inside more and dogs are photographed outside more. Clearly, this is a useful pattern that will help you do better. But this is not the pattern you actually would like to use, right? We as humans discard it because we want to learn the concepts of a dog or a cat. So in some ways now, yes, maybe like the current deep learning model outperform humans on this data set like ImageNet, but maybe they do it by cheating, and maybe that's actually, does not mean that they're actually getting human-like performance.
So what would you say about this intuition on the architecture itself? I mean, what I'm getting is, the later layers have more effect on, the layer have less effect on robustness. So you can perturb the early layers with noise, and you have more effect in cheating the system.
Yeah. Again, like I have like 5 minutes, 10 minutes left, something like this. So I want to, I'm happy to go back to this offline. It's like we don't have a good answer there, but there will be something I will show that might kind of make the discussion after the talk a bit easier. I'm happy to talk about it. I thought about it. I don't have good answers yet, but just there's something that will be relevant to this discussion that I'm about to say. And by the way, there is actually something we just played a bit with, trying to get a bit like simple theoretical model to kind of try to understand what's happening. It's like the simplest and a very toy model you can imagine is imagine you have just two Gaussians, and essentially what you would like to do, so imagine that it's infinite sample regime, so you know what the distributions are, and the only question you would like to do is you would like to do classification based on max likelihood estimates. Essentially, so what you would like to do? Well, normally what you would like to do, you would like to find the max likelihood parameters of kind of for the distribution you're observing, and of course, if you have infinite data set, then it's exactly you recover the original means and covariances. And then the way you classify, essentially what you say is, well, if you give me an input X, I just find kind of the label that makes this input X to be the most likely. Right? And that's how I classify, and this corresponds to essentially like this is the closed form expression you get, and you get like classification boundary like this. So this is like standard machine learning, nothing happening here. But now the question is, what if I wanted to do this classification, but in a way that is L2 robust? Okay? So what do I mean by this? So now when you talk about L2 robust, when you talk about max likelihood parameters, you would like to estimate like the robust max likelihood parameters. So what you would like to say is saying that, well, if I have a point somewhere here, its likelihood actually is the worst case over the whole L2 ball, like epsilon radius L2 ball around this point, and kind of the minimum, like essentially this will be, the minimum of that will be your kind of actual likelihood. So this is like a robust likelihood estimation. And then once you have this robust like parameters of the corresponding distribution, then of course the classification still works the same. Okay? But the obvious question now is like, what should actually be this, the mean and covariance estimates if you want to be robust? And somehow the intuition here is that the problem is that kind of it's a misalignment of geometries. Like these Gaussians, they are much more sensitive in this direction than they are in this direction, while this noise doesn't care. So in particular, the adversary might move your sample by relatively not much in L2 distance, but this might be a huge distance in your covariance, like in your Malhabi distance corresponding to these Gaussians. So somehow this way you can have a small perturbation of the, input that have big impact on this likelihood estimation. So actually, like when you do the computation and you think what is the best robust estimate, you end up with like actually mean is still the same, means do not matter, but the covariances matrices change. So essentially what we are doing, we have to start blending the actual covariance matrices with the identity matrix, which is kind of the covariance matrix of the geometry of the adversary. Okay, and here is like this. So you start like this. This is what you get the best classification boundary for, where there is no perturbations. But as you increase the perturbations, you kind of are blowing up this direction. Essentially, like you are fooling yourself that these Gaussians look differently than they are because you want this max likelihood estimates to be more robust to this kind of moving around this direction. So there are some observations to make. So in some ways, again, this is a toy model. We should not take it out of proportion, but just some things to make is that actually, if you just want to get best classification, you really want to take advantage of this kind of non-robust direction. Like you really want to understand that this Gaussian is kind of looks like that. But as you want to, kind of be robust, you kind of are blowing up this direction. But this, of course, comes at the price of reducing your standard accuracy. So that's this phenomena happening. The other interesting phenomena is that kind of if you think about gradient direction, if you think about, I am here at the kind of like, let's say the center of this, of this Gaussian, and I would like to find the closest point that kind of belongs to a different class. And I will just look at the gradient, which is essentially like you just go perpendicularly to the decision boundary. And kind of this will just take you somewhere there. It somehow will be a different direction that kind of if you wanted to actually go towards the center of the other distribution, which would be the natural kind of counterpart of your point. But as you become more robust, you actually these two directions align. And again, this is a toy model, but kind of it illustrates something that actually happens for standard models as well. Okay? So essentially, so this is kind of about robustness. And now the cool thing I wanted to show, especially like for the question you ask, is saying, okay, so now we know that maybe these non-robust features are something we should not be using. So the question is, so how about we use robust training to prevent our models from using non-robust features? How do these models look like? Well, it turns out to be pretty interesting. So essentially what you happen is, and again, and in the light of what we just were talking about, it should not be that surprising. Once you insist on using robust models, these models tend to be much more aligned with human perception than the standard models. So for instance, over here, like one of the popular way of trying to understand why a model made a prediction, it's a sort of very simple. Bean will talk about much more interesting ways of doing it, is kind of to use just as the gradient, like essentially at the saliency maps, which is essentially like look for each pixel and you look at its kind of sensitivity of the prediction to changing this pixel. And if you do it to a standard model, you will get things like that, which are not maybe very convincing. However, if you do the same thing to a robust model, you get things like that, which kind of are much more aligned. If you ask human to annotate what was important, this probably would be much more aligned than this to it. Okay, here there are things that are outside of the kind of the dog that seem to be relevant, and maybe there are non-robust patterns kind of showing up, but there are something about the background that kind of correlates well with the dog, and kind of you can view robustness kind of as a prior that kind of insists on kind of making the classification of the model use only meaningful aspects. And going back to representation, so now you can again look at the representation layer, essentially at the second to last layer. And now, before I told you that kind of it's very easy to find two images that look completely different, but seem to be the same at this layer. They seem to be collaged with the representation in this layer. this no longer seems to be the case for the robust models. For robust models, like the only way we can match two representations of two images, if we start from two different noisy images, is that getting something that is very similar to.
How do you reconcile that with the fact that there's just input images are 256 or whatever by 256 by 3, and representation you're looking at is like 1,000 dimensional or 4,000 dimensional, whatever it is?
Yes, so essentially
there's necessarily going to be many inputs that map onto the same output. So is it that they're truly, there still must be, is it just that this is actually a property of gradient descent, that when you, because you're finding the one that matches representation from the random initialization by SGD, right? So.
Okay. So I want to take it offline because we thought about it and there's something weird happening, by the way, how the mapping of the images into this space happens. Essentially there are, even though in principle this is high dimensional, more high dimensional, in reality, actually it seems to be much lower dimensional. So, and then essentially it seems to work the way you do, like I just described, that kind of for meaningful images, the only close by things are also meaningful images that are very close to that image. There are some parts of complete noise that things kind of behave differently, but also what is interesting is that there are directions in which there is many vectors over here that if you try to find an input that maps into them, you can't. At least we don't know how to do it. So there seems to be something interesting happening there. And remember that, here there are different reduction in dimensions happening and so on, and upsampling. So this is a complicated.
So if you took a random noise image, you feed it through, you're going to get something in that fully connected layer.
Yes.
So if you then take that and then back propagate.
Yeah. So let's talk. Since I only have 2 minutes, I'm happy to take again. I don't have a full answer, but it seems to so far work exactly as you expect, and I'm happy to discuss this more. So what I want to say is that these representations are really cool because they allow you with this to do this feature manipulations and visualizations that, again, we have seen before. This is one of the cool things, but now you can do it in an extremely simple way. You just do the most obvious things you could imagine doing, and it just works, and there is no priors needed, no regularization, no post-processing, and essentially you are really faithful to the model itself. And essentially, so yeah, you can do things like interpolations. So you can just take, two images and find a way to interpolate between them in a kind of way that is kind of, perception consistent for humans. It's actually you are morphing one image into other. So again, we knew how to do it before, but here you can do it for any two inputs, even if they are out of the data set. Normally you had to extract it from the kind of embedding of the image. There are this kind of interesting route. Here you just take two things, you find the line in between them in the representation space, and you just match everything on this path, and that's how you are getting this interpolations. You can do direct feature visualization. You can just see for every neuron kind of what essentially if I push more this neuron more, what kind of images I get. So essentially you're right. This is some frogginess neuron. This is some I think snake neuron and so on, and this is kind of it's as easy as it sounds. You can also see do the other way. You can just ask, here is a neuron, what are the images that correlate best with it, and what are the images that correlate with the worst, and again you are getting exactly what you would expect. And and similar thing you can also do feature manipulation. So you can just take an image, you find a neuron that corresponds to stripes, you increase this neuron a bit, and you are getting a tiger. Well, the dog tiger, I guess. And again, all of this, we could do it before. There was cycle gun, but now it's extremely simple and actually much more robust than how it worked before. You can also do feature level sensitivity analysis. So remember this image that was confusing, that essentially the model got wrong. Now you can actually understand why it got it wrong. So you can try to enhance the top two features that kind of are responsible for the prediction. And when you enhance them, you realize that actually this part over here, it actually looks quite a bit as a dog face. And as you know, ImageNet has many dogs, and it likes to hallucinate dogs everywhere. And that's what happened here. That's why this prediction happened. And you can do much more things. You can do actually image generation in a very simple way. And interestingly, in contrast to GANs, this actually, the more data you have, the easier it is to make it work. So this is, again, no optimization, no cherry picking. This is what you get by extremely simplistic methods. You can do super resolution. You can do in-painting. You can even do cool things like this where you kind of can take kind of, can do the kind of the AI assisted painting when you sketch something and then you ask the, the model to make it more realistic. You can also like take an input and make it more into the input of other class. So essentially you can morph, like there was a pineapple into a tiger. And yeah, essentially you can play quite a bit. This is actually, there's a demo that you can take a look at and you can play with it quite a bit and enjoy the ride. So let me just finish. And essentially, so I guess the thesis here is that adversarial examples arise from non-robust features in the data, that these patterns actually exist. Again, these features not only exist, they actually do seem to help a lot in generalization. They essentially, robust training and randomized smoothing prevents our models from using them, and that's kind of how the robustness arises. And again, and it also explains a lot of aspects of robustness, like transferability and so on. It also like enables this new capability of robustification, that you can just robustify the data set as opposed to always train a model that is robust. And again, it also makes this stronger message that interpretability needs to be addressed at the training time. But this is something you have to think from the beginning. And kind of the robust models, like if you do that, then the robust models are more human aligned. And again, there is a lot of cool stuff you can do. And then just the last point I wanted to make is that as much as I care about robustness myself, I really, it would be to me a failure if you really viewed everything I said only through the lens of like robustness and security. Because it's adversarial robustness by now, it's not only about like robustness to an adversary, it's to me really about understanding how our models learn. Okay, so in particular, what is the right notion of generalization? So we already moved to the question of robust generalization because it's clearly like more aligned with what we expect than standard IID generalization itself. And in particular, there's this question that is really just maximizing the accuracy really the right goal now? Maybe like it's clearly a more nuanced question now, and we really have to confront this question as opposed to just having one number and saying the better number you get, the better job you did. The other question is, this is also something that Ben mentioned, and I also think is important, is the distribution shift. So kind of the real problem seems to not be to how to get the IID generalization. It seems to be how to get models that are robust to distribution shift. One thing that I guess Ben is not here, but one thing I didn't agree with Ben is that actually, like, even though he shows these examples of failure to distribution shift, I think before you can say that there is a failure of adjustment to distribution shift, you have to find some way to measure what distribution shift is, right? Because clearly, when distribution shift is large, then it's not surprising that the model performs badly. Like if you suddenly, relabel every cat to a dog, you should not blame the model that it does the wrong thing. And in some ways, again, now this is something that depends on the representation. So maybe even though with this like ImageNet 101, even though to humans it seems that there should be only minimal data shift, maybe it's minimal data shift to humans, but from the point of view of robust features, maybe it's completely different. So we really don't understand that, and that's something. So before we talk about robustness to distribution shift, you should find a way of measuring it and find a way of how representations play a role there. And the other question is exactly like how do we value human alignment and interpretability? Because clearly there is a price. Like you get worst accuracy performance. So the question is how much you value it, how important it is for different applications. And somehow I view adversarial robustness as kind of just the framework for making our models better. And what better means is kind of you think of adversary as a way to encapsulate human critique. Essentially you say, okay, I don't like this kind of features to be used, and that's how I incorporate an adversary that penalizes the model for using them. And this is the way to refine the way we train our models. So that's all I have to say. We have some blog posts on our kind of website that kind of go in more depth there. Like there are some cool demos there. So yeah, feel free to play. Thank you.
I think we're way over time, so maybe.
I will be outside.
Yeah, questions outside with the coffee.
Sorry,
And so we are.